a pleasure to introduce our guest today. So, Dr. Juan José García Ripoll, right? So, Juanjo is a leading figure in the field of quantum technologies in Spain, right? So, Juanjo hold a PhD from Universidad Complutense de Madrid. Then he moved to Munich, to the Max Planck Institute with Professor Ignacio Cirac. I mean, probably you have heard about him a lot, right? And then, after 5-6 years there in Munich, so he moved to CSIC in Madrid, right? Where he leads the Quantum Information Group, QINFOC, there, right? Well, his activities are academical, of course, right? So you can read many papers in his trajectory, but also political, right? Because he's the coordinator of the Spanish network of quantum technologies, as well as advisor of the Ministry of Sciences, right? Organizing several things. So he defines himself as a physicist with the soul of an engineer, right? While he's bridging the gap between theory and industry, because he's also co-founder of the startup Inspiration Q, right? He has also many hobbies, right? Music, etc. So we have to prepare something together, right? Maybe someday. So the stage is yours.
Thank you, Jorge, for this nice presentation, and Miguel and Jorge for the patience of inviting me with these fluctuating calendars and all these things. It's very nice to be back in Bilbao. I had a lot of scientific fun here. And I'm going to give a talk. I mean, originally I designed this talk for undergraduate students. So it's going to be very easy, very full of pictures. For many of you who are experts in quantum computing and things like that, or it's going to be perhaps a little bit boring. On the other hand, it's also a way to illustrate some research lines that are quite new. Even there were papers today in the archive related to this topic, so maybe we can discuss about them. So that's the title of the talk, but it's going to be a long journey with an introduction and motivation, half of the talk of it, and then a little bit of insight in new research we are doing in Madrid. So who are we? So this is a picture of a research group. This is a research group that was created in 2018. Well, in 2005, I arrived in 2008, but it has been renovated with many new people like Diego Porras, Alejandro González Tudela, Carlos Sánchez, Álvaro, who should be there, and Tomás Ramos. So it's a group of theoreticians focused on the study of quantum technologies, of quantum hardware and applications, and also a little bit of algorithms. And we are in a very nice location in Madrid, in the center of Madrid, in the most expensive street of Madrid. We cannot live near the institute by any means. And of course, yeah, it's part of this quantum ecosystem we have there. And we are going to move in 3 years to a new institute that we will create. It's going to be called Quantum Advanced Research Center. And you are welcome to explore this new opportunity with us in the coming years. Okay? So, as I said, I'm going to make a long introduction and motivation of what we are doing. And one thing I like to emphasize is that we take for granted many ways of calculating and many technologies, as if they were the big standard, the only way to do things. And the fact is that humans have pursued many tools to enhance their capacity to acquire and process information. For instance, outsourcing part of the information to external records. These are Sumerian cones with some records of agricultural production and commercial transactions, to helping, this is very sensitive, to machines that help us enhance our implementation of algorithms like the abacus. It's a great invention that dominated calculations for hundreds of years. In this first era, what we have is extensions of our capacity to implement tasks. And we do them in these devices. The revolution comes when we create machines that compute by themselves. This is one example of those. This is the Antikythera mechanism. It's a Greek device that is conjectured to be targeted towards computing calendar events like the Olympic Games or astronomical events. And as you can see, it's just a collection of different gauges that operate and they do calculations by themselves. So in this way, we are outsourcing the computation to an external device. And this way of computing, which is mechanical, progressed through the history of humanity to a great degree of specialization with machines that were able to compute derivatives or integrals, and they were substantial, essential for doing things like ballistic aiming of projectiles in the Second World War. The whole technology of this, you can see description of these ideas in Richard Feynman's book, Are You Joking, Mr. Feynman? He talks about some period of his life where he was working on the design of these machines. And then after this way of mechanical analog of computing, we enter some kind of digitization with these computational machines operated by humans, and finally the digitization into the binary form, which is the way we compute nowadays, because it's a universal calculus that is very well adapted to be implemented in electrical circuits, and where you can go from mechanical devices, relays, to these diode bulbs, and then finally to the transistor and integrating devices that now give you supercomputing power in your pocket. This is perhaps not the best application that you can find, but there are many things that we can do nowadays just because of this new way of computing and all the technology we have created around it. And now we live in a very interesting time where this way of computing is kind of saturating. We cannot make faster processors. We cannot put more transistors, because essentially when you put more transistors, you are not making things faster. The speed of the processors nowadays is similar to the ones we had 10 years ago, and you dissipate more energy. And at the same time, we are increasing our need for computational resources, because we have all this AI boom, we have more data to process, we have new ways of computing, and the question is, what can we do about it? One way to solve this problem is to find new architectures, and people are thinking about new ways of designing processors that are more efficient, like the ARM architecture and other ideas based still on silicon. Or people are working also on how to compute using light, other ways of computing, still with the same classical formalism. And today we are exploring a new avenue in this talk, which is quantum computing. And quantum computing is now it looks quite an old idea. I mean, this is a summary of the introduction of a talk by Richard Feynman that features in his book Feynman Lectures of Computation. So during some era of his life, Feynman became very interested in understanding how computers operate, how he could use them to treat his physical problems, in particular quantum electrodynamics, and he found that some problems in physics are simply too hard for machines to grasp. And he conjectured that perhaps that's not the right way to approach the computations. The right way would be to find quantum machines that solve the problems that quantum mechanics poses that have exponential complexity. This is an idea that triggers a little bit of what we would call at the time fringe science. Scientists looking at new ways of computation, new fundamental revolutions of the way we process and acquire information that was very marginal for a lot of time. And we find, for instance, David Deutsch's contribution of thinking of how to transform the paradigm of computation, the Turing machine, into a device that moves away from the traditional tape and reading and writing device to something that stores information in quantum states and operates with quantum transformations. And in these old papers, we see the rudimentaries of what we know nowadays to be a quantum computer, a quantum circuit, universal quantum gates, and algorithms. No? So it's a very old revolution. It's 84, and at the time I would say it's a curiosity. It's something that is not taken very seriously until we find the first applications, factoring. Peter Shor comes up with an algorithm that would be of interest for the military, and suddenly a lot of money begins to pour in the field. But actually the money doesn't pour until this algorithm comes together with the first implementations. The first quantum computers. So this is one of the seminal papers in the field, proposal to build a quantum computer using atoms trapped with electromagnetic traps, trapped ions. And this evolves into different proposals to have atoms trapped with light or the trapped ions in more scalable ways. And we have a revolution where atomic physics and quantum optics show us that quantum computers are not just a mathematical construct, it's something that could become real eventually. Still 1995, it's already 30 years ago, it's a lot of time. And since then, we have had a revolution of scientists looking how to improve these setups. Now we can have experiments with hundreds of atoms controlled with high precision, even thousands of atoms that can do standing operations with themselves. Or we can move to the solid state domain, where there is a new technology, superconducting quantum circuits, which is the topic of today's talk. Okay? So however you want to look at it, we have to marvel about the capacity of the humankind to explore quantum physics on the surface of the Earth at temperatures that were unthinkable decades ago, and to explore quantum states of hundreds and thousands of particles. So it's 40 years of computation and simulation. It's a long way. More than half of our history is just theoretical developments, and only in the last decade and a half, we see the first machines operating. If you want to take something from this talk, it's going to be the part I'm going to talk now, which is how does a quantum computer work? And I don't have any ambition that you remember the rest of what I'm going to say. If anything, just pay attention to what is coming now. I'm going to discuss one technology, superconducting circuits, that came up a little bit late in the development, 2000s something. 2004 is the seminal year in which these devices begin to show very high coherence. And now it's one of the most powerful technologies to do quantum computers worldwide. So how does a superconducting quantum computer work? So I like this picture. It's an old picture. It's from 2009, I think. It was done in the group of George Martinez while he was still in University of California, Santa Barbara. He was moving to Google. After this picture, I think we haven't seen any picture of large-scale quantum processors anymore. They all become trade secrets, and nobody wants to show how these things operate. But this one is particularly beautiful because you will be able to see all the ingredients of a quantum computer in it. Okay? So what's the first thing that we need? We need qubits. And for these devices, the qubits are going to be these superconducting islands. These are small crosses made of aluminum at very low temperature. This material becomes superconductor. It means that there is no resistance, and we can manipulate the electrical states of those little capacitors with very high accuracy and very little error. And here the qubits are simply these islands where we can change the state of the qubit in terms of charge. We can have neutral states, number of electrons is equal to the number of protons, or we can have an excess of one Cooper pair, 2 electrons, that we can inject into the device. Roughly, I mean, it's a little bit more sophisticated, the description, but you can take this image home. And we can inject those things thanks to some devices here called Josephson junctions that can be used to control the qubits. The nice thing about the superconducting materials is that they have no losses virtually. They only have the coherence because of interaction with the electromagnetic field, with electrons that are trapped around it. And one thing we can do to help the computer is to filter, to simply put more superconducting material around and connect it to a ground plane, to a fixed voltage source, so that the electromagnetic environment of the qubits becomes stable. Of course, we cannot fully protect the qubits. We need to leave some room for operating them. And we do it with these filters. Okay? These are small cables. They are like the strings of a guitar. Each of them has slightly different properties, and they resonate with microwaves with slightly different frequencies. You cannot really see it from the drawing, but they are really different, okay, by hundreds of megahertz. And with these devices, what we do is we provide a path for information to come in and out of the qubit and manipulate the whole device with a common transmission line. The way it works is that now we connect all these filters to a common cable, and if the animation was right, the microwave finds the right way to the right cable and to the right qubit, and we can use this to inject energy or extract energy from the qubit. So essentially we have a superconducting device, our qubit, with 2 states, 0 and 1, they have a slightly different energy. And by illuminating those qubits with microwaves, we can make transitions from the ground state, the 0, to the excited state, the 1, or create something in between, like this kind of quantum superposition that I see here, which is a state with the same probability of being in the 0 state, no charge, or the 1 state, some extra charge. And that's a very simple concept. The only thing is that we are doing this kind of manipulations using electrical circuits that were very well known by many electrical engineers, with technologies that now we are simply bringing them down to the quantum regime. Because how to fabricate these microwaves, how to create these resonators, how to create these capacitors, this was well known, and it was used in other areas, like for instance in NMR, where you can build circuits to detect microwaves. Okay, what can we do with these qubits? We can measure them. Using the same principle, we can illuminate the qubit with microwaves, and by inspecting the phase of the reflective microwave, we can detect whether the qubit was in the 0 or in the 1 state. These are the 2 alternatives. And when we do this illumination, what happens is that we create a projective measurement. So when the qubit is in the 0 state, we always get the same phase back. We always see a 0 state. When it's in the 1, it's the same way, but with the opposite sign. And when you have a superposition, you randomly project your microwave into one of these 2 alternatives. So basically, we have everything. We have qubits, we have control of the states of those qubits, and we have measurements. So what's missing? What is missing is that we need some kind of interaction. Because the states we can create with these means are very simple. We need something to create superposition states that involve 2 or more qubits. And that is given for free in this device. The qubits are very nearby each other. In this case, there are 2 capacitors that interact electrically. And this allows energy stored in one capacitor to transition to the other capacitor, as you see here. You have one qubit is excited, and part of its energy transferred to the other qubit. The qubit, this one relaxes to 0 and goes back. There's a back and forth motion of energy. And the funny thing is that in this coherent evolution, there are points, like these crossing points here and here, where you create these kind of superpositions. And at those points, you have implemented an operation that is an entangling operation. It's the last ingredient to build a quantum computer. These ingredients, with the local controllers of the qubits and the measurements, gives you a complete quantum computer. In principle, you can do scalable computations with it. So what's left? You simply make bigger things. Find another way to arrange the qubits, improve the fidelity of your control, improve fabrication, and scale it up. Okay? Well, that's not really true. This is not enough. Okay? What happens is that you can make bigger and bigger chips, and one of the problems we have is that as you make the chips bigger, the errors in the operations I show you, they will accumulate exponentially. So we need some kind of error correction. Automatically fix the problems in these devices. I'm not going to talk about those things. I'm going to talk about another thing that happens when you grow these devices. And it's the size problem. In particular for superconductors, it may not be very obvious from the photos I show you, the chips that we build are quite sizable. You can really see them with your eyes. And if you have not 9 qubits, but you have 1,000 qubits, that becomes a very big device. Okay? So that means that's something very big that needs a lot of cooling power to be contained. And actually, this is a fridge, a custom fridge built in IBM for one of the bigger processors that they were installing. This is an old picture. There are even fridges, bigger fridges nowadays. But this is not the only problem. It's not, the chip size is not the only problem. The problem is that if you remember, we have to control these qubits. And we have to control them independently. And when you begin to accumulate qubits in a chip, you need to accumulate ways to connect to them. And so this is a processor, it's an image of an experiment from Google. I think this is the 54-qubit experiment. And you can see all the cables that go into the device. So these are hundreds of cables going to microwave generators and measurement devices that are needed to operate the quantum processor. And the reason is that our quantum processor is a little bit strange. It's not like a computer like we have here, which is very autonomous. It's closer to this. So the kind of computers we are building now, they are like a quantum abacus. They are the way where we store the information, and they are the way where we manipulate the information. And to scale this up is quite complicated. So that's one problem. The other problem is that eventually we will want to move away from these architectures and to have processors and have memories, have sensitive devices and have communication. So we need to find ways to grow these systems, but also to make them talk to each other. And this is basically the topic of this talk, is how can we network quantum devices? And how can we do it, in particular, in the scenario in which I showed you before of superconducting qubits? And it's very funny because I showed you before the paper by Ignacio Cirac and Peter Sollers, 1995, where they proposed the first architecture physical realization of a quantum computer. Well, in 1997, they put out this other paper together with Kimball and Mabuchi, where they were not only thinking about building quantum computers, but about how to connect them. So you can imagine the kind of prescience that you need to have to go from something that is not working in the lab yet to thinking about how to connect them to other devices. No? And they came up with this idea is that if I have an atom that, where I store a qubit in one quantum computer, and I have another atom that also is a qubit in another quantum computer, I can connect them by transforming the information stored in this atom into a flying photon. The atom emits a photon that goes through the cable and is absorbed at another place. The reason why this works is that we can map the 2 states of the qubit, and the 0 state and the 1 state, into having no photon or having 1 photon. And the superposition that was living initially in the atom suddenly becomes a superposition of having 0 or 1 photon with different phase relations. And all the information that is in one qubit can be migrated to the other qubit, ideally with high fidelity. And they show how to do that by controlling the light-matter interactions and shaping the photons to ensure a perfect absorption in the receiving node. This is 1997. There were no quantum computers at the time. It took a lot of time to do the first realization of these devices. This was done in the group of Gerhard Rempe in the Max Planck Institute of Quantum Optics. I was there around 2001 to 2006, and it took them already 6 more years to finish this experiment, where they trapped atoms inside big cavities so that these cavities can collect the photons emitted by the atom and inject them into a fiber that then brings the photons back into another cavity and to implement a perfect quantum state transfer. This is the operation we are doing. Quantum state transfer is transferring one qubit from one quantum device to another. And this is a seminal experiment that demonstrated that the ideas that the Tholer, Chirac, Mamouchi, and Kimball proposed, they work. In principle, they are useful. But this experiment in its own is not very useful. It's not very useful because this is just a proof of concept. So this is just one atom. They could not put more than one atom in the cavity. And each of these atoms is not even a quantum computer. I mean, it's not something that is very useful on its own. Maybe if you transform these atoms into quantum sensors or some other device, that could begin to be interesting. So what can we do with these protocols nowadays, 10 years later, when we have real quantum computers working in the lab? Well, there are 2 lines of work that people are exploring. One is to use this idea inside trapped ion quantum computers. So basically, these are the devices I showed you before, where you trap atoms with electromagnetic currents, and the atoms are confused. They are in the vacuum, floating in space, and you can use them as qubits, and you can move the atoms to one side or another and bring them in and out of the cavities to transform the information in those atoms into flying photons. And this idea has been demonstrated in the lab, at least the emission part, in the lab of Mellanium with up to 10 ions. They produce a stream of 10 photons, mapping the quantum states of 10 ions, the trap, to flying photons that could be recovered. They have not yet demonstrated networking, but it's a very good, promising avenue. The limiting problem with atoms is that for these experiments to work, you need a high efficiency transformation of information from the atom into photons. And physically, this means you have a very strong light-matter interactions. And photons are not like atoms. They are really different objects. And it's very hard to convince them to talk to each other. No? So there is physics, you could say that there is a small cross-section between a flying photon and a very tiny atom that is sometimes much smaller than the wavelength of the photon itself. So there is an intrinsic limitation here. The alternative is to work with a different technology. In superconducting quantum processors, we have the advantage that, if you remember, the microwaves that we use to control the qubits basically are the same excitations that we use to store the qubit in itself. They are simply charge, currents, and things like that moving through a chip. And those microwave currents will be the equivalent of photons in those devices. They are not very different from the energy excitations that we use to encode the 0 and 1 states of a qubit. So that's a natural advantage that gives us a very good, what engineers would call impedance match between these technologies. You can make a very strong light-matter interactions within these chips. So it makes sense to make networks with superconducting devices. So we started looking at this because in the group of ETH, they had this prototype with 2 dilution refrigerators, each of them hosting one superconducting chip with this tube, which is actually 5 tubes, concentric tubes, where the inner tube is at 21 millikelvin, and it's a perfect microwave waveguide. So what they were exploring at the time is the possibility of converting information from one processor into one flying photon, and then absorb it at the other side. And we entered this business by trying to model what happens here. And what happens here is a little bit complicated. This would be even a simplified engineering picture of the device, where we have different resonators. You have here the qubits, you have here the three-dimensional microwave waveguide and some elements like circulators and things like that. That's a little bit nasty business. As a theoretician, I prefer to think about mathematical objects that connect with each other. And we have, like, our qubit is a quantum object with 2 degrees of freedom. We have our filters, which are actually cavities, like the ones that Sirac and Sol were using, where we can store photons. And then we have an interface between those cavities and a cable, a very long cable, that goes to another cavity and to another qubit. And this would be basically our quantum link. This qubit can be part of a bigger chip that we want to connect together. And what we need to do is basically to find the recipe to do a series of things. We need to use this device to convert the information from qubit to photons, transport the photons, reabsorb the photons, and finish with a perfect state transfer. So it's like cooking. No? You need different steps in your process, and we need to find out the right ingredients for each of these steps. And what I'm going to try to convey to users is not very difficult to understand how this works, and it's already working in the lab. So these are the steps. We need to inject photons in the waveguide. That's the first idea. So we need to extract the information from the qubits, from the ground and excited states of the qubits, to having a photon or no photon. And we need to shape those photons so that they can be afterwards reabsorbed at the receiving port. We need to engineer this protocol for a perfect transfer, and then we can use it to do quantum operations, quantum gates, and optimize the whole system. So the first part is not very difficult. It's actually a beautiful mathematical problem. Essentially, you have one quantum system that can host 0 or 1 excitations, is the qubits. Another quantum system that is also going to have 0 or 1 excitations, and then a cable with a bunch of different frequency modes that can have 0 or 1 excitations. And you develop the mathematical equations for this system, and you can trace out the photons, forget about the photons for the moment, and we only need to look at the qubit wave function and the cavity wave function. And these are two couple ordinary differential equations with the constraint that the output photon is a function of the instantaneous state of the cavity. This is called an input-output theory. So there is an inverse problem. If you give me the shape of the photon you want to create, I can know the instantaneous states of the cavity, and I can know what is the light-matter interaction I have to engineer in the lab, how I have to change it in time, to perfectly transform the information from this qubit to this flying photon. So we need to design this control, the interaction between the qubit and the filter, to engineer this wave packet. And there are mathematical solutions to this problem, and you know how these wave packets need to look like, and it's a very simple engineering problem that we can do with one or more filters as the setup evolves. So this part is well understood. And then when you engineer the generation here, and you take the control and put it on the other side, but turn it around, what you achieve is state transfer. The process of emission is time reversed in the receiving node, and the photon that is created here is perfectly suited to be reabsorbed on the receiving port. And then the physics, more or less what you see here. Initially, the blue line is the state of this qubit. Initially, it's excited. This qubit releases energy into the cable. Part of this energy is passed to the cavity. It's a transient state that you see here. This is the energy stored in the cable, and then it goes into the other cavity and then into the qubit. And these are the controls we have to engineer on the left and the right ports. And you see that there is a retardation, there is a delay between both things, because the light takes some time to travel the length of the cable from one node to another. And all this is a very beautiful mathematical problem that can be solved analytically, and it works in the lab. Basically, they demonstrated this already with the setup I showed you with this 5-meter waveguide that they had. The problem is that these waveguides, they have dispersion. Basically, the frequency of the photons is not linearly related to the inverse of the wavelengths of the photons. And that creates a little bit of distortion. This is what you see here. If I send the photon, a wave packet here, it propagates with almost same group velocity, but the dispersion makes the wave packet to broaden, and it's more evident when you make the photon bounce back and forth in the cable a few times. So that means that the photon I create here with a specific control does not match the photon this node wants to receive with its own specific control. And that creates a mismatch between the emitter and the receiver nodes that leads to this infidelity curve. So if the photons are very long, this dispersion is irrelevant because they are very narrow in frequency space. Basically, they only see this band of the spectrum. They don't see the curvature of the spectrum. But as you make the process faster and faster, the photons broaden in frequency, they become fat in frequency and shorter in time. And then they see this curvature, and you get this deterioration of the fidelity. The errors grow exponentially. Still not too bad errors. 10 to the minus 4 are very good errors for transferring information even in a quantum processor, but something that we would like to correct. So what we have been doing in the last years is to operate with these devices from a realistic point of view and try to improve the operation to correct these errors and other things. The funny thing is that we can do it very easily, because if you think about the problem we have here, we are engineering a photon with one control, and we are absorbing it with a different control. But they don't need to be identical. I can either change the shape of the photon initially, what is called a predistortion, so that the photon at the end looks more like what I want to do, or I can compensate by changing the control in the absorption point to correct for the distortion of the photon through the cable. And in practice, we have to do both things if the cable is very long. And what this does is that we go from relatively poor fidelities, this is the size of the errors, to acceptable fidelities for a very long cable of 30 meters. And this works, basically. So we can even do better with some kind of optimal control approach. But this was the state of the art, more or less, in these devices at the time that we were finishing this project. Since then, there have been many experiments. These are two experiments took place in China in the same group, where they have explored the same ideas in the same fridge because it's cheaper, both with very short distances and with very long distances. And basically, they are using this as a way to interconnect quantum processors and find a way to scale up quantum technologies so that if not all your qubits fit in a chip, you can have multiple chips in the same fridge and connect them with each other. And that's a very nice approach to scaling up quantum technologies. IBM also is starting to look at these things with slightly shorter cables, and it's somehow something that has been accepted by the community as a nice route to explore in this near future. Just showing you two pictures from a different experiment, the group of Andrew Cleland and Dave Schuster. They did this idea. They first did an experiment with one qubit, sending photons into a cable, and you see how when the photon goes back, it re-excites the qubit. But then when they put two qubits, they can do perfect transfer from one qubit to another. So basically, they are sending photons from the left to the right, and at the same time from the right to the left. And the fidelity is quite acceptable. This is on a very small experiment. With our theoretician's mind, we don't need to constrain ourselves by what can be done in the experiments nowadays. Once you show that this can be done with two qubits, you can begin to think about putting more qubits. You can think about connecting hundreds of qubits to the same cable, or having multiple cables. One thing we explored that came up today on the archive it was how to multiplex the communication. The way your fiber goes to, the signals through the fiber go to your home is by frequency multiplexing. So basically, they try to use as many frequencies as possible to make the most of the bandwidth of your fiber. But another thing what we can do here in this experiment is also to use different shapes, different photon shapes. Not only the hyperbolic second I showed you before, but you have a family of orthogonal modes that you can use to distribute information in a more complex manner. And I show this here because it's part of the things we did with this project that now has been demonstrated experimentally in two groups simultaneously. In the group of Andreas Wallraff, they did this experiment with a 30-meter long quantum link, and it came up today in the archive. And a few weeks before, the group of Yasunori Nakamura did a similar experiment using similar wave packets to encode information in multiple degrees of freedom. Why is it interesting to push further these things? Well, because we need to improve the amount of bits we want to transmit, but also because those bits are needed for useful tasks, in particular to correct for the errors in the transmission. The same way that quantum processors have errors when you make gates or when you make measurements, when you send information from one place to another, you can have errors because you lose the photons, or because the wave packet is slightly distorted, and the absorption on the other side is slightly imprecise. And we need to compensate with that, transporting the ideas that people have used in quantum processors for error correction. Google is one of the leading players in this field, to the domain of quantum communication, quantum state transfer, which requires to have more photons flying simultaneously through the cable. And this is kind of the near frontier of this field, is how we can put more qubits into the same setup and do real quantum algorithms in the transmission pipeline in the near future. So it's things that probably will come in the coming years. And that's the state of the art, and that's kind of the things that people are looking at from a quantum information perspective, no? Because it's very nice, it's very beautiful to think about connecting quantum processors. Then there are other two areas. It's the ones of us who are also motivated by fundamental science. And this platform is very beautiful to do fundamental research. Okay? So this is a picture of the setup that I have in Zurich. It's a remarkable experiment. It takes a whole cellar in the physics building, all the length of building, near the parking slot. And it's a 30-meter experiment where there is this inner three-dimensional aluminum waveguide at 21 millikelvin, all the length of it. And they had to put a fridge in the middle to cool down the inner sections, but all the waveguide, all of it from here to here, is operating at a quantum regime. And what they have done with this experiment is to explore also the limits of quantum information, quantum mechanics. So, because when you have these two stations here and here separated by 30 meters, you have a delay of 100 nanoseconds between those stations. And for this experiment, that's a lot of time to do things. And so they use this experiment to explore quantum correlations, how they can be disproved from the point of view of signaling theory. So basically, they create an entangled state where they have this qubit in a superposition between in an excited state, in the one state, it has some energy here stored, and they're going to release it in the form of a photon. But they do the protocol halfway. So they send only half of the energy in the form of a photon that is then reabsorbed here. At the end, what they have is that with some probability, this qubit is excited and this one is not, and with the same probability, this qubit is in the ground state, but this one has been excited. It's a superposition of a 1, 0, 0, 1 states. It's an entangled state. And now there are quantum protocols that you can use to explore the correlations that arise from this entangled state, where you can do measurements of both sides, which are faster than the time for the light to propagate from one station to the other. So if you do these measurements very fast, in different random bases, and you correlate these results, you can find out that quantum mechanics gives you a higher degree of correlation than any classical theory with hidden variable models would explain. This is an overkill experiment. People have done this with MV centers and fibers over hundreds of kilometers, but it's very beautiful from the point of view that we are doing the same experiment with a macroscopic quantum object that weighs 1 ton and has 10,000 screws. Okay? So it's a very beautiful platform to explore this kind of physics, but it's even more interesting because it shows us a line of research that until now it was not possible. So this is a quantum link where we are exploring quantum mechanics at macroscopic scales. Now, when you begin to think about how we can scale these things, you can begin to think about networks, which, yeah, fine, you can think about them for quantum computing, but these networks are like a weird quantum system. It's like a material where you have quantum objects interacting with photons that take a lot of time to propagate, and the whole things look like a big quantum material that spreads tens of meters, or even longer. So it's a regime of exploring quantum physics and correlative phenomena and nonlinear many-body physics with devices that operate at macroscopic scales. And until now, this was something we couldn't even think about. And it's a very beautiful regime where the physics we are using nowadays to describe many-body systems doesn't work. Because when you think about a solid, two atoms in a solid are very close together. Even two atoms in the two sides of a solid, they are very close together. Their interactions are almost instantaneous. But here you require hundreds of nanoseconds for information to propagate. Interactions are retarded. And that gives you a kind of physics that we don't even yet have the tools to explain. So and those are the things we are now exploring in our lab. And I'm going to close this talk with this picture I like a lot. So Martinez came to Spain to visit us 2019, just as when they did this quantum supremacy experiment. I don't care if that experiment is not a quantum supremacy experiment or not. What I like is this remark, which is the fact that 40 years after the first ideas of quantum computing, we are doing physics in the lab that it was really unthinkable for the fathers of quantum mechanics. And that's a very beautiful time to live in, and it's for you to take advantage of. So thank you.
For the talk. Questions?
Hi, thanks for the talk. So I have a question. So I understood that each of these, well, boxes or nodes where you only had one qubit I don't know if in the theory, at least theory, can you send entanglement if you have more than one qubit with this photon idea also?
Yeah, we can put many qubits. We did studies of how you could put qubits with slightly different frequencies. Formally, we could do hundreds of qubits and make them interact simultaneously through the same link. And that can be used, as I said, to send information redundantly in error-corrected codes. It can be used to transfer more sophisticated entangled states, correlated states of the qubits, or it can be used to distribute information and create correlated states between these two big ensembles of qubits. So all these things are possible, in principle.
And I guess that, for example, if you want to send an entangled state from the qubits that you have somewhere, it would mean that you need the same number of photons or something like that, and entangled between them, all of them? Or?
Well, in this paradigm, we are doing a unitary transformation. Where was it? So basically, what we are doing here is that we map the quantum state of the qubit into a quantum state of the photons. Mm-hmm. And this is a unitary map. Okay? So all the information in the qubit is transported into the information of the photon. If you have 10 qubits, you map the whole 10 qubit states into up to 10 flying photons. So it's a one-to-one mapping. You can do better, more interesting things, if you don't map all the information into flying photons, but you leave the photons entangled with the emitter nodes. That's the Bell inequality experiment. They only emit half of a photon, because with some probability, the information stays in the qubit. And that's the way you can get light-matter correlations that is used for some protocols.
Okay, so yeah, my question was that what you said is a one-to-one map. So
yes.
I was thinking maybe there's two ways of entangling the photons to represent the same state that you had. I mean,
yeah. So you could do. So this is a superposition between vacuum and having one photon. You could have superposition between photons in two frequencies, or you can have more sophisticated states. And people are thinking, for instance, in mapping the state of a qubit to a Schrödinger cat state or the electromagnetic field. But that's quite difficult to do. There are some no-go theories about the coupling schemes that people are engineering, but that's another idea. So people have now very beautiful ways of encoding information in the electromagnetic states of cavities. These are very good qubits. They are very long-lived. They can be error-corrected. And now what they can do is they can map those cat states into flying electromagnetic wave packets with up to hundreds of photons. So those things can also be done.
Thanks.
More questions?
Thank you very much for the talk. I had a couple of questions. Well, the first one is that you mentioned that you have qubits, then you have a cavity, and then you have your waveguide. And you mentioned that the qubits are tunably coupled to the cavity.
Yes.
What kind of tunable coupler is there, or is it path
Well,
shaping? Or?
there are many schemes.
Okay.
In Zurich, what they do is that the qubit doesn't have enough energy to populate the cavity. They are off-resonant. Okay. So what they do is they provide the energy with external microwave so that they can take still one photon from the microwave, a little bit of a photon from the qubit, and that creates a photon in the cavity.
Okay, but they are like capacitively coupled directly.
They are capacitively coupled, but they are
microwave
not resonant.
Yeah.
And you assist it with an external drive.
Okay, okay, thank you.
But there are simpler ways to do that. Right?
Okay, yeah. And you mentioned that the waveguide is made of aluminum also?
Yeah, this is a big chunk of space-grade aluminum.
Okay.
It's macroscopic.
Okay.
It's overkill. Other people are doing these things with coaxial cables.
Yeah, that was my next question. Like here, you need like cryogenic temperatures all the way through the
Yes,
waveguide.
but
So this
with the
seems like really expensive.
With the coaxial cable, you also need cryogenic temperatures.
Ah, okay.
Because otherwise you have photons there that disturb your protocols. The thing is that these cables, they also have losses. They are more lossy than fibers. And the reason why they use these 3 waveguides is that, I mean, it's very bulky, but inside there, the photon is basically isolated from everything. It's a very thick aluminum shield. Inside there is nothing. So only the photon moving through. The problem is that it's very difficult to match the field in the tube to the field in a chip. And that's a huge engineering task that is not fully solved. And it's the reason why these experiments that I showed you before have like 80% fidelity, and that's something they are trying to improve.
Okay. Okay, thank you very much.
Okay, we have more questions from this side, right?
Thanks, Juanjo, for the talk. My question is, the original idea of quantum state transfer by Dirac and Soller, and Maguchi and so on, basically they are proposing to send the state in using a pulse of light. Can you make it, instead of one pulse, like distributed in 10 or 2 different wave packets instead of a single wave packet?
In principle, you could. And you don't even need to do a wave packet. There are, for certain sizes of the cable, it's more advantageous to do a very long, continuous transfer of information. You don't really make a photon shape, it's the field all the time connected.
Yeah.
So it really depends on the circumstances. Multiple wave packets, I haven't seen it, except for the fact that of this entanglement distribution, when you send a fraction of a photon, or other protocols that we studied where you want to distribute, you want to entangle a qubit with different qubits. So you send a fraction of a photon that goes to this qubit, another one that goes to this qubit, another one that goes to this qubit, and that's another way to do entanglement at larger scales.
Yeah, and that you already did with Ricardo and so on.
Yeah, entanglement distribution we did, yeah, because it's a very trivial idea, but we haven't explored something more sophisticated.
Okay, thanks.
Okay.
Yeah, nice one. I have to be scared, no?
No, you shouldn't be. Well, it's not fair. Well, thanks a lot. But it's not fair that I hadn't had time to actually look at the archive today. So
I mean, I saw it in LinkedIn, so I don't. I didn't even have time to read it either. Yeah.
But so actually, this experimental with the guys in Zurich.
Yes.
One thing I was wondering, because of this special correction, if you have this triple line waveguide, you don't have much dispersion. So actually, this is because you are doing matching to an external.
This experiment is cheating. It's done on the same chip. There's no dispersion. Beautiful, 100% transfer. Or the coaxial cable that we saw before. This one is also almost dispersion free. So those are okay.
So it's just the matching between the internal, the strip line of the chip and the outside. Okay. So the thing they have in Zurich, the one you have mentioned with Andreas Wallraff and company, it's 30 meters, so I guess that's coaxial-like?
No, that's a tube. It's a metallic tube.
Okay.
I'm sorry, I forgot to put a cross-section of this. There is a square tube in the middle, I think it's centimeter size, and there is then a layer of tubes to shield it. But the one in the middle is a 3D commercial 3D waveguide for microwaves. So basically they patch together waveguides. And then it's made of aluminum, so when you cool these things down, it becomes superconductor. They don't need to think about it. The problem is that you have a square tube that now you have to connect to a chip. And the engineering of the device that brings the field from here to the chip is very sophisticated. And it's not working as well as they would like. And that's the most challenging thing for this platform.
Also, they have used it for some other purposes I have seen, because this survey said that...
Yeah, they've made a lot of papers. So that's one. They did the Bell experiment. They are doing others with remote measurements. For instance, they have a protocol where this qubit creates a photon, goes here, touches this other qubit without doing anything, goes back, and this qubit now suddenly knows the state of this other qubit, and they get entangled. And that's still unpublished, but it's already working too.
Okay, and the question was about the temporal modes you are using in order to do the multiplexing.
Yes.
Because as soon as you go to much higher modes, you are going to need many more actual frequencies, which will be taking you out of the usual approximation. So
Where was it?
I haven't done numbers, so I don't...
I mean, the problem is not so much chirping, it's the engineering of the wave package. This requires a very precise microwave control, and, well, they can do what they can do. And even this is not fully optimized, because we have the device, but we don't have observability into the device. So I don't know what is the exact frequency of the cavity. I cannot do experiments. I can only look at the qubits on the sides. So it's not perfectly engineered yet. It's subject to improvement.
Okay, so maybe we have time for an additional question. The students, now is the opportunity.
Don't be shy.
Have a point more in nuclear and particle physics. Essential question.
Exactly. Okay, I have one, right? Very general, right? So somehow you have presented. It's like, I mean, I am talking now about the application, a way to scale, right? So it's like building like a small processing units connected by links, somehow, right? So is this the accepted way by the community of scaling this type of technology?
No, it's not the accepted. It's one that people in circuits like, because you can do things with more chips in the same fridge. But I think it's not only a matter of scalability, is that, I mean, your computers, it's not just everything on a chip. You have many devices that talk together. And as I showed you before, this is like an abacus. Your processor is your memory. You want to move away from this. And these ideas can also be applied to other areas. Extended quantum sensors, for instance, is an area of research where you can improve in the fidelity, or you can improve in sensitivity. For instance, when you look at stars, you could use distributed sensors to improve your sensitivity by studying the correlations. That's done now by classical means, but it could be done by quantum means. So I think it's just something that the field has to do, regardless of whether it's applicable for quantum computing or not.
I see. Okay, and then, so you have talked about different technologies, so trapped ions and superconducting circuits that, okay, I could follow, thanks. But could you give us your opinion, for instance, about the last experiments? I mean, it's a different technology. Your opinion about the technology that people these neutral atoms with atomic tweezers that Lukin did in December 2025.
People now can trap 3,000 atoms for very long times. There are high fidelity quantum computing experiments with error correction with, again, hundreds of atoms. I think that those are very beautiful routes to follow. Those platforms, they don't need connectivity right now.
They don't need.
I don't think they need it, because if you have 3,000 atoms, that's more than qubits you can have faithfully put in a chip right now. Maybe at some point they will be constrained by the experiment and the traps and the vacuum chambers and the lasers and everything, and they will want to do this kind of connectivities. But as I discussed before, doing this with atoms is an order of magnitude more difficult than with solid-state devices.
Okay, thanks a lot. So if no more questions, I think we can thank Juanjo again. Thanks a lot.